Hello everyone. In this video, we will be looking at two important avionics data bus standards. ARINC-629, a multi-transmitter digital communication bus used in large commercial aircraft, and the Commercial Standard Digital Bus, or CSDB, widely used in general aviation and retrofit transport aircraft. We will explore their architecture, protocol mechanisms, message formats, error detection methods, and real-world aircraft applications. ARINC-629 is an advanced, multi-transmitter digital data bus developed by Boeing and introduced on the Boeing 777. It was adopted by the AEEC in 1989 and later implemented on aircraft such as the Airbus A330 and A340. It replaced the older ARINC-429 standard and enabled a more flexible, scalable, and deterministic communication architecture in modern avionics. Earlier systems like ARINC-429 relied on single-transmitter, point-to-point links. As avionics became more integrated, especially with fly-by-wire systems, these networks suffered from wiring complexity and limited data flow. Boeing initiated the DATAC program, or Digital Autonomous Terminal Access Communication, which evolved into ARINC-629. Its goal was to create a multi-transmitter bus with deterministic timing and terminal independence. Now we will see on the system overview of ARINC-629. ARINC-629 allows up to 120 avionics terminals to share a single, linear twisted pair bus at 2 megabits per second. It uses Manchester 2 encoding for robust, self-clocking transmission, and it requires no central bus controller. Every terminal can transmit or receive independently using distributed timing rules. When an LRU needs to transmit data, the terminal controller retrieves the 16-bit parallel words, attaches the correct label, and converts them into a serial stream. The serial interface module converts this into Manchester-encoded doublets, which are inductively coupled onto the bus through the current mode coupler. All listening terminals examine the labels and store only the data meant for them, ensuring efficient communication. Now we will see the main hardware modules of ARINC-629. The terminal controller handles bus access, protocol logic, message framing, and Manchester encoding. The serial interface module manages the digital-to-analog conversions, waveform validation, power switching, and coupler channel selection. The current mode coupler provides a non-intrusive, impedance-controlled interface that injects and receives doublets while supporting redundant channels for reliability. The stub cables connect each LRU to the coupler and can reach lengths of up to 57 feet. The main bus cable is a 130-ohm twisted pair that may extend nearly 300 feet, as seen in the Boeing 777. Couplers are mounted in panels within the main equipment center for simplified inspection and protection. Go through the block diagram of ARINC-629. Now we will see the timing behavior, access mechanism, and protocol modes. ARINC-629 uses a time-based collision avoidance method governed by 3 timers: the transmission interval, the synchronization gap, and the terminal gap. Together, these ensure that only one terminal transmits at a time, without requiring a master controller. This distributed control protocol guarantees deterministic communication essential for flight-critical systems. The transmission interval defines the period between transmissions from the same terminal. The synchronization gap is a global idle time before anyone can transmit, and the terminal gap adds a unique offset for each terminal. Depending on the relationship between these values, the bus operates in either periodic or aperiodic mode. The basic protocol treats all terminals equally and supports both periodic and aperiodic messages, even at full bus loading. The combined protocol introduces priority levels to ensure that critical periodic data always transmits first. The Boeing 777 uses the basic protocol for most buses. Now we will see the message scheduling and messaging structure. Block mode scheduling supports smaller periodic updates and uses a combination of X and Y moduli to vary message length. Independent mode scheduling supports a wider range of update rates with constant word string lengths. Both methods optimize bandwidth while ensuring predictable transmissions. Each ARINC-629 message consists of 1 or more word strings. Each word string begins with a 20-bit label word, followed by up to 256 data words. There are 4,092 available labels and more than 1 million addressable data words. PSSP and PPSSP sync patterns indicate the start of each message. Manchester 2 encoding uses a mid-bit transition to represent each bit and embed clock information. This greatly improves noise tolerance and synchronization. The bus uses differential doublets to reduce electromagnetic interference and maintain reliable communication in harsh aircraft environments. ARINC-629 includes parity checks, timing checks, waveform validation, and redundant controllers. The serial interface module checks both transmitted and returned signals, and the terminal controller monitors message formats and timeouts. Faults are isolated quickly to maintain system integrity. The Boeing 777 uses 11 ARINC-629 buses, 3 flight control buses, 4 system buses for hydraulics, avionics, and propulsion, and 4 AIMS inter-cabinet buses. The AIMS computers also act as gateways and centralized maintenance processors. Couplers and bus assemblies are mounted on protected panels along the aircraft fuselage. This arrangement allows easier maintenance and reduces wiring complexity while improving system reliability. ARINC-629 delivers deterministic timing, fault tolerance, and stable throughput even at full utilization. Its autonomous terminal architecture avoids single points of failure, making it well-suited for flight-critical applications. ARINC-429 is simple but limited to point-to-point links. ARINC-629 introduced multi-transmitter deterministic operation. Modern aircraft now use ARINC-664 AFDX, which provides Ethernet-based, high-bandwidth, virtual link communication. Together, these standards outline the evolution of commercial avionics data buses. Now let us go through CSDB. The Commercial Standard Digital Bus, or CSDB, is an asynchronous, unidirectional broadcast bus developed by the Collins General Aviation Division. It operates at 12.5 and 50 kilobits per second over cable lengths up to 50 meters, with built-in fault protection. CSDB supports one transmitter and up to 10 receivers on a single bus. Bidirectional communication requires a separate bus. Gateways interface CSDB with systems like ARINC-429 by performing protocol conversion and timing management, while ensuring minimal latency. CSDB supports continuous repetition for periodic updates, non-continuous repetition for conditional data, and burst transmission for triggered events. Burst mode repeats the same message 16 times at about 20 updates per second, similar to fault annunciation systems. Each byte in CSDB has 11 bits including start, stop, data, and parity bits. Messages begin with an address byte, followed by an optional status byte and data bytes. A frame starts with several A5 hexadecimal synchronization bytes. Because of overhead, the effective throughput is lower than the theoretical 4500 bytes per second. Parity is used for each byte, while burst transmissions include an additional checksum. Receivers store the first valid block with correct checksum. Hardware monitors parity errors, frame errors, and overruns, while software may apply additional checks for safety-critical functions. Integration includes physical, logical, software, and functional aspects. Physically, CSDB follows RS-422A and supports 10 receivers with electrical protection. Logically, data patterns and message lengths must be consistent. Software defines sequencing and update rates, while functional integration ensures correct interpretation of address, status, and data fields. CSDB uses NRZ modulation with differential signaling. Logic states depend on the polarity of the A and B lines. Rise and fall times, input capacitance, and transmitter drive levels are tightly controlled to ensure reliable operation across all LRUs. With only one transmitter allowed, CSDB simplifies integration, but it does not define system-level architecture. Collins controls the specification, and deviations require formal approval. Designers must consider full electrical loading even if the installed system initially uses fewer LRUs. Testing includes internal checks like parity and checksum validation, and external checks defined in DO-160 environmental standards. Black box simulators emulate LRUs to verify timing, message formats, and error handling. Full compliance must be demonstrated during system certification. CSDB is widely used in general aviation and regional aircraft such as the Saab 340, ATR 42 and 72-8, and several Embraer and Short Brothers models, along with many rotorcraft. In summary, CSDB provides a simple, robust, and low-cost communication method ideal for smaller aircraft, while ARINC-629 supports large commercial platforms requiring deterministic, multi-terminal communication. Thank you for watching this presentation on ARINC-629 and CSDB. I hope this session provided clarity on these two critical avionics communication standards.